Hello, everyone. My name is Stefan Angelkovic, and today I will be talking to you about how you can simulate your own galaxy on a computer and see if some intelligent civilizations emerge there and maybe expand, colonize space, and communicate with each other. So to start off, I'll give you an overview of what is required to have life in a galaxy. First, water. Without water, we can't have the chemical reactions that are needed for life to function, and we cannot have proteins do their job. So water is very, very important. But when I say water, what I mean is liquid water, not ice, not vapor, liquid water. Then we have 6 important elements here, some of them already present in water. These are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 elements compose 97% of our bodies, and they're very important. Here I have a little cartoon of them just to give you an idea of how big they are compared to each other. Now, minerals, most notably iron, calcium, and magnesium. Iron is very important for cell respiration. So when we breathe, we need iron to capture that oxygen. Calcium is very important for maintaining the cell structure. So it makes sure that everything that is in the cell that helps us work and live is working properly. Well, basically think about it as important ingredient for our traffic in our cell that everything works fine. Then there is magnesium, which is very important for stabilizing our plasma membranes. So if we don't have enough magnesium, we have a lot of static electricity there that's not going to let the cells communicate the way they want to. And finally, we need heat. If it's too cold, you can't have anything. It's just dark and dead. So where can we make this life? Where can we have this life? It's got to be on a planet somewhere. This planet is going to be orbiting a star, and the star is going to be somewhere in a galaxy, like this one. Now, not everywhere in a galaxy and not everywhere around the star you can expect to find life. Why though? Because too far from the star, you don't have enough heat on a planet to sustain life. And then too close to a star, it might be burning hot. So we need to find something in the middle. And the astronomers have called this place a Goldilocks zone, where the water is liquid. So it's hot enough to make it liquid, but not too much to evaporate. The size and position of the Goldilocks zone, it really depends on the star. The hotter the star is, the further out you want to go. The colder the star is, you want to get closer. Like a fireplace, you want to get close to it to get warm. So here's an idea of the planets that astronomers have discovered, just to show you that we already know that there are planets in our galaxy that fit in these Goldilocks zones, that are close enough but not too close to their host stars. If you look at this picture, you can see all these planets, and between the yellow and the blue line is what would be like most likely the habitable zone. So these planets that are between the yellow and the blue lines, they're like either they might have some life, or maybe they would be interesting to be colonized by us in the future. And these planets between the red and yellow lines, they are, with a lot of optimism, they could harbor life. Like maybe if we had like super fancy equipment, maybe we could colonize them one day. And you can see that Venus doesn't fit into either of these two because it is too hot on Venus. And there is strong greenhouse effect. Okay, so the planets, if you go to the right, you are looking at planets that receive less starlight and hence less heat from their host stars. If you're going from bottom up, you are looking at the planets that are orbiting hotter and hotter stars. So, okay, now we know about the planets orbiting the stars, but what about the positions of the stars? Does that matter? Like, where should the star be in a galaxy to have most probability to find life there? Well, we don't want this star to be too close to the center of the galaxy, because too close to the galactic center, we have too many giant Jupiter-like planets. They're like huge balls of gas, basically almost stars. And when there are these huge balls of gas, you can't really put life there. It's just going to be floating. Everything is going to be floating around and you can't put the pieces together. And then too far away, you don't have enough elements that are heavier than helium. So the stars are mostly composed of hydrogen, which is the smallest element, and like 90% of it, and then 9% of the stars is basically helium. And this is also an element that is too light and too simple. We need some elements that are more complicated to allow for construction of life and to have all the building pieces we need. So we can see that in a galaxy, we also have some sort of a Goldilocks zone. And we want to look at this ring around the center, but not very close to the center. And we can only expect to have life there either somehow emerge on its own or colonize these planets around there. So what about when? There's this thing that we haven't really seen aliens yet. And the question is why though? So when we study the galaxy and where the life could potentially emerge, we want to see within this galaxy, where could the life be and when could it start so that they wouldn't have been able to reach us by now. Because maybe if the life started too early, they could have communicated to us. But if the life starts too late, then how come we are here? So we don't want to look at the planets where the life could only form very recently. We don't want to look too close to the center of the galaxy because, as I said, too close, this is the left part of the figure here. That's where you have too much heavy element abundance. And and then we don't want to look too far out because too far out, we don't have enough heavy elements. So we want something in the middle and we want something that is not too late. When you take all these into account, scientists have studied this like in the early 2000s, and they reached the conclusion that life on our planet started later than they would actually expect. If you look at the position of the sun, you will see that it's at the top of this green zone. But on average, you would expect something in the middle of this green zone, which would be some 6 billion years ago, while the life on Earth here is basically, I mean, the planet is basically before 4.5 billion years ago. So we have a big question here. Where are the aliens if we haven't seen them? And back in the 60s, it was a very popular question. They had some sci-fi shows started, such as Star Trek. They had famous sci-fi movies studying the exploration of cosmos and potential encounters with different civilizations from different planets. And in 1961, they started this conference where they wanted to discuss why don't we see any life in the space? What should we do to communicate with aliens if there are any? Should we expect that there are aliens? So Frank Drake wrote this little equation here to give an idea of whether it is likely to find another alien life somewhere in space. And he wanted to estimate the number of planets where we could potentially find life forms that could communicate to us somehow via some sort of radio. So he started the equation with this R star, which is the star formation rate, that tells you how many stars are being formed every million years. And then he multiplies that with the fraction of stars that host potentially habitable planets, this FP. So let's say that maybe 50% of the stars have planets that have solid ground. And then you multiply that with NE, which stands for the average number of planets that are orbiting these stars that have solid ground. So if we look at our solar system, we have 8 planets and 4 of them have solid ground, Mercury, Venus, Earth, and Mars. And then 4 of them are gas giants, Jupiter, Saturn, Neptune, and Uranus. So looking at that, we would say, okay, on average, if we consider our solar system to be a representative of an average star system, we would say, okay, NE would be equal to 4. We expect 4 planets around this star to have solid ground. And then among these 4 planets, multiplied by the number of these stars, we want to look at the fraction of them that actually can support life. And now, out of these 4 planets, only Earth has considerable amounts of liquid water. So maybe we could add Mars to the list, but definitely not Venus. So we might say, okay, our FL is a fraction of these planets that have ability to accommodate life. So we would say 2 out of 4, or FL would be 50%. And then out of these, we have a fraction of planets that have intelligent life emerging. So looking at solar system again, we would say, okay, but out of these 2 planets, only Earth has intelligent life. So we would say 1 out of 2, again, 50%. And then you want to multiply with the fraction of planets among these that have some sort of communication that can go all the way through galaxy. And we're probably talking about something like radio. So you can say, well, okay, it's 100% here. We have radios. We can send like these signals out in space and wait for someone to respond. But take into account that we didn't have radios forever. So we only had radios since mid last century, like mid 20th century. So you could have intelligent life for thousands of years without having radios. So this fraction is going to be something lower than 1. And then finally, we have this L, which is basically the time we expect them to communicate. So let's say we started communicating, trying to emit these signals into space in 1960s. So we would say, okay, we have maybe 60 years of attempting to communicate with aliens. But 60 years compared to the lifespan of the civilization, it's just a fraction of time. So when they started estimating this, because there are no good numbers, some of these things could be, 1% or 90%. It's really hard to tell what are the right numbers. So the results they got based on what numbers they plugged in, they varied from 0 civilizations, meaning that even us being here is very unlikely, to hundreds of millions of civilizations, which means that we probably have super intelligent aliens everywhere, and they're just too bored with us. They don't want to talk to us. We don't know. But this is how SETI started, Search for Extraterrestrial Intelligence. There is an agency that's trying to figure out if there is alien life and can we communicate with them and like establish contact, maybe learn something from them, maybe teach them something, and so on. So what can we do if there are some aliens out there and they don't want to talk to us and we can't find out anything about them? Well, the best thing we can do is run computer simulations. So that's how scientists are studying this topic. They try to think, okay, if there is some alien life out there, how they would behave, what could we expect? And what if they're just too far away? So that's why our signals haven't reached them yet, or their signals haven't reached us, or they reached us maybe too early on when we didn't have a good enough equipment to pick up these signals, and they thought we're just undeveloped and nothing interesting is happening here, so they just moved on. So how can we run these simulations? There is something called probabilistic cellular automata, and it's something like chess in a sense. I'm going to explain these 3 big words to you. First, probabilistic means there is some probability that one thing will happen or the other thing. And then it's like in a chess, you never know which move your opponent is going to make. You have to wait for him. And then cellular means that you're dividing something into a bunch of cells, and each cell is having its own moves. So it's like chessboard. You look at these fields, each field would be one cell. And then automata means there is a set of rules that are being followed, and the only thing that is not fixed is which rule will be taken into account. So you have this knight here. There, on this small chessboard, there is 6 different options for him. Like he can go into either one of these 6 positions next. But which one it will take, that's where the probabilistic comes into play. We get to roll the dice. Imagine having 6-sided dice. You roll it, and then you see where it's going to go. So for our coding session here, to give you a little bit of taste of how scientists are simulating this, we're going to have some sort of chessboard, and then each cell is going to represent one part of the galaxy, or we're going to have one planet with likely life possibilities. And each cell will have a state of 0, 1, 2, or 3. 0 will be arid planets with no life, picture desert. And then 1 will mean you have simple life like bacteria there. So nothing major is going on, but there is some life form. And then Level 2 will mean you have complex life like plants and animals, and maybe they can't use some advanced technology, but they're living beings there. And then level 3 will be technological civilization, which has capacity to travel in space and potentially colonize other planets. So how we're going to play this game? We have these transition rules. That's where the automata part comes into play. We have evolution. So if there is no life, life can emerge there by accident or some divine intervention, but molecules can get assembled in such a way that you get some sort of bacteria. And we will have some probability of that happening on uninhabited planets. Then there is always probability when you have bacteria that somehow they will evolve into more complex beings, and that you will reach plants or animals at that stage. And then after that, maybe some animal species will evolve further and learn how to use tools and develop technology, become intelligent, and become able to colonize other planets. So these are some of the possibilities, evolution. Then we can have a catastrophic event, which will wipe out life or just make some sort of setback. Say, for whatever reason, we lose our ability to use internet, and then all the knowledge is lost. And now we have to live in wilderness, and we don't have technology, but we are still some sort of animals. So there is still complex life. It's just that we're unable to go to space. Or we have nuclear war and wipe out everything, something like that. And then we can also have colonization as the third type of the rule, which means that if we have this intelligent and technologically advanced life on a planet, maybe at some point they want to expand, and they want to go to another planet that is not too far away, and they'll board the spaceships and move on to their next adventure. So what these catastrophic events would be, you go from simple life to no life, or from complex life to no life, which would be some sort of wipeout. You can have asteroid impact. So regardless of what we do on the planet, an asteroid could hit a planet and make this disaster. Then, I mean, it already happened. So you can have super volcanism. For some planets, you can have too strong volcanic activity, too many volcanoes, and that might wipe out life there. We already had huge volcanic eruptions in our history, so that's how we know about this. You can have climate change. This is something that's above our heads right now. That with the climate change, maybe the plants and the animals cannot adapt to the new conditions, and they might die off. And then you can have biosphere collapse, where similarly to this climate change, when some species dies off, then the species that's feeding on them can die off. And then you can have a whole chain of like chain reaction of destruction of life there. So, because we really need each other on this planet. And then you can have parent star flares. So all stars have their electromagnetic activity, and they have their own volcanic eruptions, so to say. And these eruptions might emit these high energy particles that might hit a planet and cause irreparable damage, or just cause damage. Like flares like this could knock out our satellites and cause power outages, etc. Now, if they're, for whatever reason, too strong, they might even have enough radiation to kill off these complex life forms. And then all of these apply if you have technologically advanced civilization. All of these risk factors are there. But technologically advanced civilizations, they have another risk factor, and that is the wipeout due to technology itself. We can make nukes and use nukes and kill off life, make everything radioactive, cause cancer, etc. We can also make maybe some robots that might rebel against us, or any form of mechanical and so we can be the cause of our own doom. That's why we need to be very careful when we're developing technology and know what we're doing there. And then instead of wipeout, we can also have a setback. Just go down 1 or 2 levels, but not eradicate all life. So in this scenario, for whatever reason, maybe we're just not good enough to wield this technology, so we just destroy it. And we go back to living in nature as our ancestors did 100,000 years ago. So this kind of setback would be going from technologically advanced civilization to simple life or complex life, but not wipe out all life. And also, for whatever reason, complex life can go back to simple life. But what about colonization? This is a third type of the processes we have here. So if we look at our fictional chessboard, you have a field, a cell, where you have a technologically advanced civilization on the left, and it wants to expand to another planet in the nearest sector. So it can form a settlement, and it can expand throughout the galaxy. So now the neighboring cell that we're colonizing, it might have no life, or it might have only bacteria, or it might have complex life. It doesn't matter, because the life will be there. The most complex life form there will be our settlers. Now, I'm not going to go into details what would happen if a technologically advanced civilization tries to colonize a planet where you already have a technologically advanced civilization. There is probably going to be some war, and now that will make simulations much more complicated. But we're just going to ignore this as a very, very remote possibility. So what about our chessboard? Well, there are 2 most common ways you can split your galaxy plane. You can use hexagonal lattice, like what we have here on the left side, which is very nice because you can basically make this form that looks like a circle, and you might be like covering a circle pretty well. While if you want to do a circle on this rectangular lattice, where you have square cells, your circles are going to look like this. So if you move the center of the circle a little bit, you go from the left shaded figure to the right shaded figure, and it kind of looks very different. It looks like it rotated, but actually it's just different because you didn't rotate it, you moved it up a little bit. So we can see that these square cells aren't that good, but they're simple enough. So we're going to use the square cells just to give you an idea of how this works. And then if you want to play more with it, you can try to see what would it look like with hexagonal cells. So how are we going to do this simulation? First thing about the simulations of something that happens over time is that you have to determine what your time step is. You need your time step to be small enough so you're not missing any major events, but you don't want to make it too small so that your simulation runs forever. So if we're talking about these things in the galaxy, we want the time step to be something that's very, very, very long. So we probably wouldn't be using something like seconds or minutes, because imagine looking at your watch and you're like, oh, so no aliens contacted me yet. And then you look at it again 5 minutes later, oh, no aliens yet, and so on. And you just post to social media 5 minutes later, no one contacted me yet from outer space. And you can write messages all day long and nothing's going to happen, because this is not the relevant time scale for this. You want to look at something that's more like millions years, because nothing is going to change within 5 minutes here. So for our simulation here, to make it short enough, we're working with 5 million years as a single time step. So every time we need to roll dice to see what's going on, it's another 5 million years in this cell. How long will the simulation be? Well, 10 billion years. That should cover it up, because the best estimates from astronomical observations for the age of the universe are around 14 billion years. So assuming that early on you didn't have the galaxies formed like this, and the age of galaxy would be somewhere around 10 billion years for Milky Way, we would say, okay, 10 billion years is probably good enough an estimate. And the major question, what do we expect to see in the end? So here's an example of how a simulation might end up if you are keeping track of where the civilizations are. So whenever civilization is colonizing neighboring planets, you write down that this planet that is colonized has the same color, has the same number as the civilization that colonized it. And if you look at it, you can see a huge empire here in the top left corner. And then you can see some like smaller civilization, like smaller countries, like the pink one on the right side and the one on the left side near the bottom, near the red one, and so on. So we can see that we have a couple of like galactic islands here where we have these civilizations. And now the question is, can we do this? Can we simulate this? So it's demo time. So we want to make a small galaxy here. And just to give you an idea how it looks like, I'm just first going to make a 9x9 chessboard, so to say. So if you look at the numbers here, we can see this -1 in the center. We can see this ring of zeros. And then there is kind of ring of -1s around it. And then we have -2s in the corners. We can see this more visually. So here's our little galaxy. We can see that yellow color is number 0. This kind of green is -1, and navy is -2. So if this is our little galaxy, basically navy is the empty space outside of the galaxy. Green is the part of the galaxy where we don't have a habitable zone, and yellow is our habitable zone. Now, we're not going to work with this little galaxy. It doesn't even look like a circle. We're going to do the same thing, but now we're going to have a bigger galaxy. Now we got our bigger galaxy, and you can see that the lines here are way smoother than they used to be. And you can see nice circles. Okay, so the yellow ring is our galactic habitable zone. That's where we expect to have some planets that might harbor life, where potentially we could make some sort of colony, and we should be somewhere here in the yellow ring. Okay. So the question is, now that we have this kind of galaxy, how can we study how its evolution is going? How can we study the dynamics of life there? So for the next step, we need to define some numbers. We're going to use some equation for probabilities of changing the states. Let's say from technologically advanced civilization, something happens, some catastrophe, and we go all the way back to no life on the planet. There is some probability that this can happen, and we need to calculate these probabilities. So this probability is going to depend on certain time intervals that are expected lengths of time for how long you need to wait before this catastrophe will happen. So let's say you don't expect to have an asteroid hit Earth every day. So the time between two asteroid impacts would be something on the scale of maybe hundreds of thousands of or millions of years. When you want to calculate the probability that a catastrophe happens there, you're going to compare the time since the last event, since technologically advanced civilization was developed on this planet until now. And when we divide that time with the time that's characteristic for this kind of catastrophe, or how much time you would expect a technologically advanced civilization to spend before they eventually destroy themselves. So we're going to define these characteristic times for switching between level from 0 and 1, 0 and 2, 0 and 3, and so on. So first, I'm going to fix a couple of these values that I know should work and make sense. So I'm going to put these numbers here. And I'm going to write some comments so that I can remember what these numbers have to do with. So first, these are characteristic times for evolution. Okay. Then I'm going to put characteristic times for catastrophic events. So these are when the levels go down from 1 to 0 and from 2 to 0. And these numbers, we really don't know how big these numbers should be. So the idea is that you can play around with some of these numbers and see how changing the time between, like the expected time between the two catastrophic events of the same type, or changing the time needed for a civilization to advance from, let's say, from complex life to technologically advanced civilization. Changing these times can tell us how these processes are affecting what we see on the galactic scale, whether maybe evolution going too fast will allow us to colonize whole galaxy, or maybe if we don't evolve too fast, but then we are making some sort of accidents that can wipe out all life, maybe we'll never reach that point where we can colonize the other parts of the galaxy. So eventually I will leave this to you so you can play with this and change the numbers and see how you can get different results. Now I want to put the characteristic times for inhabiting the planets. I can call this settling. I want this T23 to be different from the other T23 that we have here, which comes from evolution, meaning you have life that just advanced on this planet. That is a different thing from life coming from another planet and just settling down. So I need to use a different name here. Okay, so now we have all these characteristic types, but then there is another parameter, another number that's required for our equation. And this number is called amplitude. And it allows us to make sure that certain events are fairly rare compared to some other events. So I'm going to put these amplitudes. These are also things you can play with. And one of the nice things about working in computer is that you get to copy a lot of your work and recycle it. So the next one is the block of here, catastrophic events. So here I need 1, 0, 2, 0, 2, 1. I'm going to copy this. Okay, now we have all these parameters. Before we can move on to simulating what's going to happen to the galaxy, you're going to need one more ingredient here, and that ingredient is going to be a function that's going to check if a cell has neighbors that are ready to settle in this cell. So we're looking at the cells that are around our cell. We're going to use this function to also count for the cells that are habitable. And let's say that in each cell, we have one planet that fits all the criteria that you can have life on it, potentially. So in this yellow ring, we want every yellow square to have, say, one planet. Just to simplify the way we're talking about this. Okay, so to check the neighbors, that's it. This is our function. Okay, and now we're ready to build the main part of our simulation. Before we start looping and iterating over the course of the history of the galaxy, we're also going to need some sort of clock. And the clock is going to monitor how long each cell has been in the state it's been. So for the clock, we're going to have every cell have their own clock. And this clock is going to count how many turns has a cell stayed in the same state. So let's say in a certain cell, which basically means on a certain planet, we have simple life go into complex life, and now we reach the complex life phase. We want the clock to reset to 0 and then count how many turns has this planet stayed with complex life before it changes through maybe technological advanced civilization, or the life gets wiped out or changes state in any way. And because we need one clock for each cell, we're going to use another table that has the same shape as our galaxy. And in this table, we're going to store these clocks. So it's 100 by 100 table. Okay, now we have all the ingredients and we can go to the simulation. For the simulation, we can also use another map. I'm going to call this a world map. And the reason I want to do this is, okay, I can instead copy my galaxy. So right now, this world map is going to have all the same values as the galaxy. It's going to be 100 by 100 table. The difference between the galaxy and the world map here is going to be that the galaxy is going to tell me whether a cell has 0, 1, 2, or 3 for the level, or -1 saying it's a part of the galaxy but not in the habitable zone, or -2 saying, oh, it's not even a part of the galaxy. So we have 6 different options. But for the world map, I want to see it as kind of a political map of the world, where you see kind of like different countries. Now, these different countries are going to be more like galactic empires. As one civilization advances and starts settling down on different planets, we can get it to grow into like a bigger empire. And we want to store this just to see if a certain civilization expanded into the universe. Okay, so in the world map, every time a new civilization is founded, it emerged from complex life. I'm talking about technologically advanced civilizations. Every time we will use a new number for this civilization, and wherever in the world map you see this number, that's the territory that this civilization is occupying. That's the planet that belongs to this civilization. Okay, and I'm also going to have a civilization number that's going to start at 0. Obviously, no civilizations in the beginning, but then as we get new civilizations emerging, we're going to increase this number. And eventually, we can look at the number and see how many civilizations were found during the course of our simulation. Okay, now we have everything ready and we can run our code. One thing about the simulations is that they can take some time, and that is why we are printing these intermediate statements. So now our simulation has reached 1 billion years, and that's at 10%. While we're waiting for the simulation to be finished, let me tell you what you can expect. So in the end, we're going to have the same galaxy display with this ring that represents the habitable zone. But within this ring, we're going to have some points that are brighter and some of them they're darker. And these darker points are going to represent simple life, while the brighter points are going to be complex, and the brightest points are going to be technologically advanced civilizations. This is going to be our galaxy map. But then for the world map, we're going to start from 0, which is going to be navy blue, and we're going to go all the way up to yellow for the latest civilization. So basically, the brighter the spot, the later the civilization appeared. Okay, actually, this was 5 billion year simulation, not 10. So my last print statement is kind of incorrect. But you can see here, so this is the galaxy map, and I'm going to click this. It's going to open the larger map here. You can see that we have 100 rows, 100 columns. The points go from navy for outside the galaxy up to yellow, orange-ish for the level 3. This is the highest level we have here. And you can see that our simulation kind of expects a bunch of technologically advanced civilizations around. Now, we can't really tell how many of them are here, because all of the planets that have technologically advanced civilizations are marked with the same color. This is why we're going to use world map. But I wanted to show you here that there are still some spots with basically no life. There are some spots with simple life, etc. And there are a lot of green spots that correspond to level 2 or the complex life. So it's very colorful. Okay, now we're going to go back and we're going to respond. Do we want to see the plot of the world map? Well, yes. I'm just going to press enter. And here's the next plot. So to make it larger, now looking at this plot, we can say there is probably around 300 civilizations that have appeared over the course of these 5 billion years. The yellow points are the latest civilizations. We can see some in the bottom. We can see one point here surrounded with all these green ones. We can see one at the top, another one at the top near some green ones. We can see that these early civilizations are mostly on the left side, but there are some on the right top side. And we can see that all of these civilizations kind of went around this circle that we remember being the galactic habitable zone. So whatever we got here, it really belongs to our galactic habitable zone. It passes this so-called sanity check. So this is how our galactic map looks after 5 billion years. Adding another 5 billion years of simulation by increasing the number of steps from 1,000 to 2,000 would give us even more civilizations. Now, if you want to play with the parameters, we can go back and change some of these characteristic times, increase them. Increasing the catastrophic event times means that catastrophic events are rarer than what we assumed here. They happen less frequently. And if you decrease them, then that means that you expect catastrophes or disasters to happen more often. The same goes for inhabiting the planets. If you increase these times, you're going to slow down settling across the galaxy. And then you can also increase the amplitudes. That's going to increase the probabilities of life evolving and so on. Or maybe you want to decrease the catastrophic events. And finally, if you want to check how many civilizations we have, you should add a print statement and then civilization number. You can put something like that, and it's going to print our results. I'm going to change the characteristic times for evolution to reach technologically advanced stage. I'm going to increase this to 50, and I'm going to rerun this. You can access this code, and then you can play with this. You can change these numbers. You can play with this. When you rerun it, you will get different civilizations, maybe fewer, maybe more. Maybe you will see more simple life, maybe you'll see more technologically advanced civilizations. There are countless possibilities. And the way scientists are now studying this possibility of finding life, alien life somewhere else, is basically they're running like all sorts of different scenarios, and then they are studying how the likelihoods of finding some aliens change based on these numbers, and then they're trying to connect these numbers to some experimentally measured values and make their theories be somehow grounded in what we see in the universe around us. So basically, because we can't really make aliens contact us, what we can do is pretend that there are some aliens out there, and if there are, we can see if maybe them sending the messages to us, can we have their messages reach us or not? So if we have a galaxy like this, where basically everything is densely populated, we would expect that there is a bunch of aliens that might be trying to contact us. But maybe the numbers for our galaxy are different, and that means that we don't have as many aliens, or maybe we don't have any aliens at all. So it really depends on what kind of numbers we have here. You can play with these numbers and see what you get. Thank you for watching.